ايش؟ شو على الشارع؟ صلحوا انتوا حماد لحالكم. هالجاشو.
أنا عرفت الطابق بس ما عرفت. أنت حبيبي.
تفلت وتظبط يلا.
أنا فيك هيك. أنا فيك.
يلا يمكن بدفع. وذ شوكليت. خلص بس حكيهم بالدار العربية يعني. هذه شغلاتنا.
Good morning, everybody. Looks like people are trickling in. We'll give another couple of minutes before we start. Okay, good. Looks like everybody's ready. Okay, looks like we're about at capacity, so why don't we go ahead and get started then. So good morning, it's nice to see you guys again. Let's see, let's take care of old business and new business before we dive into the physics content for the day. So I'm liking this format of writing on the screen and uploading the PDF notes to you guys. I hope that's working okay for you so far. So you'll see from last time, you guys are seeing the screen, right? I didn't forget to share. Yeah, okay, cool. So you'll see from last time, there were the lecture notes that I uploaded ahead of time, and then there's the printout of what I actually made it through in class. So like these notes have stuff that we didn't make it to on Tuesday. This is what was actually written on the screen on Tuesday, and that makes my life a little easier because I can literally copy and paste the stuff that we didn't get to last time, and that is now the beginning of lecture 3's notes for today. So hopefully that makes my life a little bit easier. Does this format work for you guys? You want to like click yes or no or yes or something, the writing on screen? Okay.
Yeah, I think that works better for me as well.
Okay, great. That makes my life easier. I have to do only like 2,000% of the work for 1 hour of class instead of 3,000% of the work. So that helps me.
In general, it's good, but the font writing, when we print it out in the sheets, it seems very small.
Yeah. Okay, I'll have to think about what to do about this. If you're looking at it digitally, it should be like vectorized so you can zoom in pretty far without losing resolution. But yeah, on the printout, that's probably difficult. I think what happens, so let me drag this over here, for example. So when I have the page in OneNote and I'm writing on it, I can extend it as far to the right as I want. And so if I want to make a comment next to something that we already have, I can always do that. But the flip side is when I write over here, where is it? If anywhere in the document I like add a little comment that drifts over to the right, it sort of zooms out the printout enough to fit it all on one page. So I have to think about if there's a better way for me to do that. I will try to not like write a bunch of stuff off to the right. I think if I avoid writing a bunch of stuff side by side, then that should help with the font size problem. Please keep me in the loop about this. There's probably things that I can do to make sure that it doesn't render too small when I convert it to PDF. Okay, let's see. So other old business, let's see. I think I had already posted the relevant important links last time, including the next couple of sections of Shankar if you want to get ahead for today and for next week. The assignment, I made one small modification on the homework. It was pointed out to me last time that I had assigned it and asked for it to be due this coming Monday, which is actually Labor Day. So I pushed it back for one day, and so now you see it's due on the 8th. I didn't bother going in and changing the PDF. The PDF still says due the 7th, but I added a little comment here that it's not actually due the 7th, and you can have an extra day to do that since it's Labor Day. What questions do you guys have for me at this point? Hopefully you've had a chance to at least glance at the homework. Do you have questions? Is there anything unclear? Have you found any stupid typos that I made when I wrote the assignment?
So number 4?
Problem number 4, yes.
When you refer to the vector v on part, on the second part?
Part B?
Yeah, is that just
yeah.
It's a random vector, right? But can we assume that it's expanded in the basis, on the, not on the basis, but on the linear, on that I basis, or?
That's a good question. Does someone know the answer to that question?
Well, I said, I assume it's not at first, and then I guess that's what the problem is asking us to.
So, yeah, basically that's the right statement, that if the basis is complete, then you know for sure that you can expand any vector such as v inside the vector space v in that complete basis. So in some sense, what you're showing is that this is a complete basis.
Okay.
So the test that you're being asked to show here is that okay, so I guess part B doesn't require this comment about V. That's really for part C.
Part C.
Yeah. So if there is another vector V that is in the vector space V, so vector little v that lives in the vector space big V, could it be independent of this one? Could it be linearly independent of this set?
Okay.
And so that's equivalent to saying, is that set of exactly n vectors a complete basis for the vector space V? And so essentially the whole of this problem is the argument to prove, at least up through part B, that it is a complete basis, and therefore there can't be any other linearly independent vector in the space.
Okay.
I don't know if I answered your question or if I just talk in circles.
I think, yeah, it's good.
Okay.
Yeah.
Any other questions or maybe mistakes that I made when I wrote the homework? It would not be the first time. I'm especially curious to see what you guys think about problem 3. This is not your standard, like, do some math and solve a problem for me exercise. I want to see if you can verbalize or explain in words what the math is telling you. If any of this is not clear, or if you think you understand what it means, but you have a hard time expressing it in words, just let me know and we'll figure out a good way for you to write something up and submit this. Okay, I think that's it on my list of old business, new business. Is there anything that you guys want to bring up to me or anything that I forgot to mention? Okay. If not, then let's continue our discussion about linear transformations. All right, so previously, so we talked about bases, specifically as we just discussed in terms of problem number 3. So we talked about complete orthonormal bases. And maybe just as a comment here, that problem 3 is equivalent to showing that, let me write it this way. So for problem 3 from the homework, this is essentially proving the theorem that says that in a vector space of dimension n, any set of n orthogonal vectors is a complete basis. And again, Shankar sort of states this as a theorem in the text, and he outlines the proof. But wait a second, sorry, this was problem 4, not problem 3, excuse me. Yeah, Shankar basically states this in a couple of places in the text and then offers some paragraphs that sort of illustrate the proof, and I wanted to walk you through that in a little bit more detailed fashion. Okay, so we talked about complete bases, and then we introduced the discussion of linear operators. Linear operators or linear transformations. And we wrote these as matrix elements of a transformation omega between sets of basis states. So you pick some complete, usually we assume complete orthonormal basis, and then you express the action of operator omega in terms of what it does to those basis vectors. And related to this, we talked about inserting a complete set of states, or inserting a complete set of basis vectors. Inserting a complete set of basis vectors, where we wrote the identity operator 1 is equal to the sum over projections onto a specific basis vector I. That gives you a number, that's a dot product. And then after you project it onto basis vector I, you make a vector out of it again by putting it in the direction of I. And if I have a complete set of states, then this operation is just a language to describe the vector. It doesn't limit the kind of vectors that can exist. So that's what this would say. Okay. So today we're going to continue this discussion talking about the adjoint operator, a sort of alternative view of what the operator omega does to kets. It can be reinterpreted as acting on the prods. And then we'll finally introduce the eigenvalue and eigenvector problem, which is going to be one of the most important exercises that we will repeat 500,000 times throughout this class. Okay, so let me say a few words about conceptually and then mathematically what the adjoint is. Okay, so for the adjoint operator, we've seen that if I take the action of a linear operator omega between two states, or between two vectors, let's call it A and B, that I can insert for free a set of complete basis vectors. So formally, I can write this as A times the identity operator 1 times the same omega times another identity operator 1 times the state B. And we can use the fact that for any complete set of states, or a complete set of basis vectors, I can write this as a sum over those projection operators. And I can do that for both of them. Sum over J, J, J. And when I insert this, then I get any matrix element that I want to calculate is expressed in terms of my basis vectors. So this is sum over I and sum over J, A, I omega J, J, B. And so I just want to point out that this formulation is symmetric between what the operator does here, and its relationship to both the ket on this side through that repeated summation index j, and its connection to the bra on this side through its repeated summation of the index I. Just a comment about how to interpret what these quantities are. So that JB quantity is the projection of vector B onto basis vector J. Projection of B onto basis vector J. So this quantity is the one that we're familiar with. This is the component. You might call it vector B's Jth component. And that's expressed through this projection of B onto J. The reason I'm telling you this is to also interpret what's happening on the bra side. If the bra A is a one form, this is a way of taking a vector and converting it into a number using the dot product or the inner product. If I take that mapping where I project onto a vector A and I take its overlap with basis vector I, then this is similarly the component, you might call it A sub j, or maybe even A sub j dagger, or A sub j star, for reasons we'll talk about in a moment. This is the component of the bra A. So for the most part, we talked about components of vectors, but you can also talk about components of dual space vectors or components of bras. And the point that I want to make here is that this matrix can be equally well interpreted to be acting on the kets because of the repeated summation over J, or to be acting on the bras through the repeated summation I. So another way to say this is that when I have that matrix element I omega J, and this thing is contracted with J, B, and A, I, one way of saying is that this index is an index that exists in the dual space. That's telling me something about the bras in the dual space V star, whereas this index is one that lives in the vector space, the original vector space, V. So when I sum this thing over I and J, this is just equal to the matrix product. If I interpret the bra as being a row vector, so let me write A projected on 1, A projected on 2, dot, 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 A projected on N. And now I'm multiplying by a square matrix for the operators. So this would be 1 omega 1, 1 omega 2, dot, 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 2 omega 1, 2 omega 2, dot, 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 on down the line. And omega 2, dot, 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 excuse me, 1 omega n, 2 omega n, dot, 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 n omega n. And then the multiplication by the vector B's components looks like a column vector or column matrix. So that now I have 1b, 2b, dot, 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 nb. And so to further make this point about the indices and which space the indices live in, if I write the matrix multiplication explicitly, then I'm taking the ith component of that row matrix, which sums over the ith component of that square matrix times the jth component, which is then contracted with the column matrix at the end. So the point is that the operator, especially when represented as a matrix transformation upon the basis components, the operator is symmetric and can be understood as transforming the bra or the ket. So this is what I mean when I talk about the adjoint. I talk about the partner operator omega that is now acting on the dual space. So we say if omega acts on the kets in the vector space V, by which I mean if I have some vector V and I hit it with the operator omega, then I return back a new vector V prime. If omega is the operator that acts on the kets, then we define the adjoint operation omega dagger is the partner which acts on the bras. You might say it's the partner, you might say it's the dual operator which acts on the bras. So what does this mean? I want to re-express this formula for the bras in terms of the kets. So now I want to define, if I have the corresponding bra V, and that bra now acts on the adjoint operator omega dagger, then this is defined to give me back the corresponding bra V prime. So definition, if V prime ket is the answer you get from letting omega act on V, the ket, then the definition is that V prime bra is the answer you get when omega dagger acts on the bra V. So conceptually, these are different things, but they are mathematically related to one another. They are related to each other by the property of skew symmetry that tells us how to take a dot product and flip the order. That's what's going to let us transform bras into kets. So I can define either one of these things in terms of their components. We said if V prime equals omega V, then the components of V prime can be written I V prime equals I omega V. All I did was sandwich this vector on the left with the basis vector I. And now I will insert a complete set of states. Complete set of basis vectors, I omega J, V. And let me write the summation explicitly. So now J is being summed over. So now this is handy because everything is expressed in terms of dot products, and I know how to take a dot product and flip the order. Recall that we had skew symmetry as one of the generalized properties of the inner product. Skew symmetry, where we said the overlap of A with B is almost the same thing as the other order, the overlap of B with A, up to complex conjugation. And that complex conjugation is what's going to relate omega to omega dagger. So how do I determine what the components of the bra are? So we said if this is what omega does to a vector V, then what does omega do to the bra? So we had, okay, let me maybe write it up this way. So I want to know what the bra V prime is. The bra V prime I can expand in terms of its projections onto a basis. So let me write this as, which index did I need? Let me call this K so I don't repeat any indices. So this is V prime K, by our insertion of completeness. Skew symmetry tells me how to relate the component with V the bra and K a basis vector ket to the other order. So this is equal to K V prime conjugate by skew symmetry. So this is equal to sum over K V prime complex conjugate K. And I know what K V prime is. The projection of V prime onto some basis vector, here we call it I, is given by this expression. So the dual vector V prime is equal to we had sum over k to begin with. Now I have also a sum over j. So now I can't forget to complex conjugate this expression. So now I have excuse me, not I, but k. K omega, what is it? K omega j conjugate j v conjugates times k. Okay, to simplify our life, let's relate this back to the definition of omega dagger. So v prime bra is defined to be whatever I get when the adjoint of omega acts on the bra v. So my left-hand side is equal to v times omega dagger. I'd like to express what omega dagger is in terms of omega. The easiest way for me to do that is to multiply both sides on the right by a ket. So let's see, I've got a whole bunch of indices floating around. I've got j and k, so let's use I. So now if I multiply both of these equations by the basis vector I on the right-hand side, now on the left I get the component of omega dagger, v omega dagger I equals sum over j and k omega j conjugate, j v conjugate. And now after I project things, I have k projected onto the basis vector I. What is this overlap?
Kronecker delta.
Kronecker delta. Very good. That follows because of our assumption that this is an orthonormal basis. If it's a Kronecker delta, then I can use this to kill the summation over k. Kill sum over k, set k equals I. So now it reduces me down to v omega dagger I equals sum over only j, k omega, k is now equal to I omega j conjugate, j v conjugates. Okay, very good. We're almost finished. The only other step is now to insert completeness here on the left-hand side, right? So I have a matrix element with still the vector v on the left-hand side, whereas on the right-hand side, I've pulled out v in terms of components already. So I want to pull out v in terms of components on the left-hand side also. So if I insert 1 equals sum over j, j, get very used to this, you'll be doing it a lot. You end up with vj, let's see, sum over j, j omega dagger I equals sum over j, I omega j conjugate. And let me make my life simple again. I will use also skew symmetry to turn this overlap of j with v back the other way, vj. And now you can see why I did that. I have the same components of v on the left-hand side and on the right-hand side. So if I subtract them both to the left-hand side, then I have sum over j, a common factor with the components, v's component with basis vector j, and I'm left with the difference, j omega dagger I minus I omega j complex conjugates equals 0. So this is again, by the way, equivalent to a matrix equation. So this looks like v on 1, dot, 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 v on n, multiplying the matrix, which is, let's write it this way, 1 omega dagger 1 minus 1 omega 1 complex conjugate, and so on, equals, this is actually, I guess, a matrix of zeros. So what this equation is telling us is that for any components of any vector v you want, that vector times this matrix must be equal to 0. And this can only be satisfied if the matrix itself here is equal to 0. This is the statement of linear independence. If all of my basis vectors are linearly independent, then there's no way that I can add them all up to get 0 with some coefficients, unless the coefficients themselves are exactly 0. And so what this is telling us is that basically, even though I've got, let's say, this X, the delay between when I click on the thing and when it figures it out so I can start writing is really annoying. Okay, even though I still have outside this extra summation and some unknown coefficients, none of that stuff matters because these things are linearly independent, and therefore I can conclude that the thing in parentheses must be 0. And that's what gives me my expression for omega dagger. So I omega dagger j is equal to j omega I complex conjugates. And so even though the adjoint of a matrix or the adjoint of an operation is in principle like some conceptually totally different thing, it's not independent. So the adjoint transformation down. If I'm distracted and it's hard to write, this is why. He's getting in the way. So the adjoint omega dagger is equal to the transpose complex conjugate. So it's omega under transposition and complex conjugation. So maybe in more familiar terms without bras and caps, this says that the matrix omega daggers ij component is equal to the original matrix omega's component ji with row and column swapped and complex conjugated. So we will refer to this operation as the adjoint. That's what it means in practice. Take whatever matrix you have representing the kets, transpose it in complex conjugated, and that will give you the bras. That's equivalent to our condition of skew symmetry. You will also hear other terms associated with this. So you'll also hear the phrase Hermitian conjugates. That means the same thing. Okay, so Hermitian conjugate is related to the definition of a Hermitian matrix. So a Hermitian operator or a Hermitian transformation or a Hermitian matrix is one where the matrix and its adjoint are identical. So omega dagger equals omega, which in terms of components we said means omega dagger ij equals omega ji complex conjugate, and this is equal to the original. Let me maybe write it this way, ij. So these three lines of the definition, omega ij dagger is omega star ji. If omega star ji is equal to the original omega ij, then the matrix is Hermitian. So, i.e., something like, let's say, I don't know, I have 1 on the diagonal, and if I have something on the off diagonal, if I have x plus iy here, then I need x minus iy there. So that when I take the transpose, I flip which things are on the off diagonal, and I complex conjugate. So this matrix is Hermitian. Similarly, an anti-Hermitian matrix is one that changes minus sign when you take the adjoints. Anti-Hermitian is one for which omega dagger equals negative omega. or in terms of components, this condition means that omega ji star, which is the definition of omega ij dagger, is equal to negative omega ij. Hermitian matrices or Hermitian operators will play an extremely important role in quantum mechanics. Anti-Hermitian operators can also be useful. Usually you can just take the extra minus sign and write it as a Hermitian matrix times a factor I. So if I have a matrix H equals H dagger, which is Hermitian, then if I take that same matrix and I multiply it by the complex number I, then IH dagger is equal to I complex conjugate H dagger. H dagger is already equal to H because H is Hermitian, so that's minus IH. And so this is anti-Hermitian.
No.
So anti-Hermitian matrices can be important sometimes, but they can always be sort of expanded or converted back into Hermitian matrices with an explicit factor of I, if that's useful. The transformations that I want to talk about in great detail are unitary transformations. So a unitary transformation is one that preserves the inner product. And we will show this momentarily. And the unitary transformation, by definition, means that the adjoint is equal to its inverse. So that means these are matrices U such that U dagger is equal to U inverse, which is equivalent to saying U dagger U is equal to the identity transformation. And it doesn't matter what order you multiply them, U dagger. So in the homework, you work out a specific example of transforms like this. Problem 1 is called the special unitary group, SU2. If I drag this back over for a second, this is the explicit representation of unitary transforms that have determinant 1. So as we work out here, so special means that the determinant is equal to 1. Unitary is exactly what we're talking about now, that the inverse of the matrix is equal to its adjoint, U dagger. So you will check that, in fact, this does work and that it has these various properties. So unitary transformations are super important. We already hinted at this already, but you should think of unitary transformations as a more general version of a rotation. So we mentioned previously the group, let's say SO2 or SO3, SO3, these were rotations in 2D and 3D. And we said if I allow the matrices to become complex, then orthogonal for real matrices, the orthogonal condition is the O in these groups. That means you're talking about rotations. We said orthogonal matrices are ones for which the matrix O, not dagger, but transpose, O equals 1. This was orthogonality, or orthogonal matrices. You can see that this is the same thing as being unitary if the matrices are made out of real numbers. If complex conjugation doesn't do anything, then the adjoint is the same thing as the transpose. So the unitary groups unitary transformations, i.e. SU2 and SU3, are the generalization to complex numbers. Generalized rotations using complex numbers. And that's why we end up with u dagger u is equal to 1.
Which level?
Okay, so why are unitary transformations like rotations? Because rotations preserve lengths. If I have a vector of some length, I rotate it around, the length of the vector is unchanged by the rotation. That's equivalent to saying that the group SON, SO2 or SO3 of rotations has determinant 1. The determinant of the matrix is related to changing the magnitude of the vector. And if the determinant is 1, the magnitude doesn't change. So we saw rotations, i.e. SON, preserve the dot product or preserve length. For real vectors, so these were orthogonal transformations. And so unitary transformations i.e. SUN preserve our inner product, our generalized inner product AB. So now let's prove this. By proving this, I mean, I want to show that if I have a new vector A prime that is obtained from A by a unitary transformation, U times A, where U is unitary, and similarly, B prime is also obtained by the same unitary transformation U from B. That's really important. It has to be the same transformation of both vectors. Then what we want to show is that the dot product of A prime with B prime is the same as the dot product of A with B. And this is what we want to check. And the way that I will check this is by expanding the ket B in terms of U, and expanding the bra A prime in terms of U dagger, because we know how these things relate. So what we have is A prime, B prime equals, let me write out what this is. This is A prime. A prime is obtained by the unitary transformation U dagger, because U acted on the ket A to give me the ket A prime. So in the dual space, the adjoint operator U dagger is the one that takes A prime, that takes A and turns it into A prime as a block. And the vector B prime is obtained by the same unitary transformation U acting on B. So you can do this proof as fast or as slow as you want. At this point, you can immediately write down the answer, just in purely abstract notation, because we know that the transformation U and U dagger together are the identity operator 1, 1 by unitary. And if this thing is equal to 1, then that's just equal to A, B, and the proof is done. If this is not totally obvious to you what the hell this means, it might help to expand things in terms of components where it looks like a matrix product instead of some abstract operator living in some complex n-dimensional vector space. If that is helpful, then you can consider inserting a complete set of states. A U dagger I, U, B. And now this looks exactly like a matrix product. So this is A1 dot 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 AN dagger. Excuse me. I forgot to write the unitary operator, that's why. U dagger dagger 1, A, U dagger 2, ... Microsoft Windows has its uses, but it also really annoys me sometimes. Okay, times the column matrix 1 UB 2 UB ... here. If I insert more complete sets of states, I can make it look like a bigger matrix product, right? So this is helpful. It doesn't quite get me far enough where I can say the matrix U dagger times the matrix U is equal to the identity matrix. To do that, I need to insert another complete set of states here and here. And then I will get U by itself. Right now, U still has A and B attached to it. So maybe let me insert completeness 2 more times. So let's write this as sum over I and J and K. Okay, for consistency, let me make this K. As I inserted I the first time. K, U dagger I, U, J, B. Okay, and now I'm happy with this, because this is a matrix multiplication that only involves U and U dagger. It doesn't have anything to do with A or B anymore. And the repeated index here is I. So you can see quickly that the sum over I, K, U dagger I, U, J. This is equal to a matrix product where I take U daggers Ki elements, sum over I, times U's Ij element. So now this is like just basic matrix multiplication. And this is the place that you use that the product of these two together is the identity matrix Ij. That's another way of saying that this is equal to the Kronecker delta Ij. And if this is equal to the Kronecker delta Ij, then if I carry this down, A prime, B prime equals sum over, let's see, we perform the sum over I. Now I have sum over J and K. A, K, delta Ij. Sorry, that's why this looked weird for me. Delta Kj. K was the external index here on the left. J is the external index on the right, so I better have Kj left over after I sum over I. So this is delta Kj, which makes me happier. And then now this is JB. If I sum over the Kronecker delta, now I have the final answer, which again agrees with what we had before. This is sum over K, A sub K, K, B. And since the sum over K of this projection operator is equal to 1, again, the identity operator, this is the long way of showing that A prime, B prime equals A, B. So either of these is fine. I know which one I prefer. Once you are comfortable working with the abstract notation, then I think, writing a proof like this will go very easily for you once it's easy to look at the browsing text and see what that's telling you in terms of vectors. If it's not clear, my recommendation is to always expand everything in terms of a complete orthonormal basis, and then you will have matrix products that are easier to wrap your head around concretely. Okay, any questions about this so far? We've talked about the adjoint as a conceptually different object. We've talked about how to show that the adjoint, the unitary transformation preserves the norm. And we've talked about a couple of different ways to calculate things like this, sort of very abstractly or by components. Any questions so far? Nicholas, did you have a question?
I was going to ask a question, but I just thought of it, so I figured it out.
Please ask the question anyway, even if you've already answered it. Others might have the same question.
I was just kind of thinking of how it wasn't exactly a question, I guess. I was just clarifying something in my head between real numbers versus complex numbers.
Yes.
But after going through the different operators and how they just kind of annihilate to the identity matrix, it just ended up making sense.
Okay. Yeah, so I think the real case is a little easier to wrap your head around. So if you get confused, always benchmark yourself against like the real number case where you're talking about pure rotations instead of these more abstract unitary transformations. Okay, any other questions before we move on? Okay, I just want to make a comment about active versus passive transformations. Active versus passive transformations. So if I have a matrix element, something like, let's see. Yeah, so let's say I start off with an operator omega, and I can quantify it by specifying its matrix elements omega ij, and consider how it transforms under a unitary transformation U. One way to view this is to say that I am taking an actual vector j and I am transforming it into a different vector j prime. So the active transformation is the interpretation that says I have some vector j and this is turning into a new vector called j prime, which I obtain from the original vector j by unitary transformation. So this is a picture where it says, I don't know, you had some vector j, and under the action of unitary transformation u, my old vector j became a new vector j prime. And in going from my input vector j to the output vector j prime, I have transformed j under the transformation u. Under an active transformation like this, what happens to the matrix elements of omega? So my j prime equals u times j, my I prime equals u times I, which, because of the adjoint definition, implies that the bra I prime is equal to the bra I times u dagger. So what does this do to the transformation? What does this do to the matrix omega? Impact on matrix elements of omega. So this is like answering the question, what does omega look like after the transformation? After transformation. So the new matrix elements in the transformed phases are I prime, omega, j prime, and then I just express I prime and j prime in terms of u. So this is the original I, u dagger, omega, u, the original j. So this is the expression. It doesn't matter what point of view you take. This is the answer either way. But the active transformation or the active picture kind of looks like this grouping of the operations. It's like saying u dagger transforms basis vector I. I still have the same operator I started with omega. And then u transforms the basis state j. So the active sense is in this interpretation, that u transforms the states. My operator is the same as the one I started with. Same operator, and these are transformed states. States or vectors. The math is the same for this transformation no matter what, but I can reinterpret the same process as the states being the same, but the operator omega changing. So this is the passive picture, passive transformation. Is everyone still alive? Okay. Sorry, I heard a crash from the living room and thought my son might have broken his leg or something. Okay, the passive transformation picture still says I prime omega j prime equals I u dagger omega u j, but the grouping is interpreted differently. You could think of this as the same basis vectors I and j, but now a different omega, u dagger omega u j. And so this quantity is like an omega prime, a new operator, u dagger omega u. So same math, different interpretation. You could read that as I changed what the state is, or I changed physically what the vector is, but I measured the same thing. Or you could say I measured a different quantity in the original state, like God handed me a quantum state represented by some vectors. I don't touch it, but I can ask the question about what I would measure in that quantum state, measuring it in one basis versus measuring it in a different basis. So these are equivalent and they both have their uses. For future reference, you will see these two interpretations associated with what are called the Schrodinger and Heisenberg pictures of quantum mechanics. So for future reference, the active transformation picture is one where your vector or your quantum state, when we talk about vectors being quantum states, psi, actively changing, right? So this would be my quantum state psi goes to a new quantum state u times psi, and this is called the Schrodinger picture. In particular, you talk about the unitary operation that gives you time dependence. So there's one special unitary operator. So unitary time dependent evolution. So you can think of this transformation as u of t. It tells you how to take the original state you had at t equals 0, evolve it forward in time using the Hamiltonian, actually, to produce a state at some later time. So this active picture is one in which time evolution is actually changing your quantum state as a function of time. The opposite picture, the passive picture, is the one where if God gave me a quantum state, it stays in that quantum state, but the thing that I'd like to measure is time dependent. So this is called the Heisenberg picture. Where it says my omega is now transforming and becoming time dependent. So that now I have u dagger of t omega u of t. And this would give me a time dependent operator that acts on time-independent states. Both of these things are equally valid. Both of them have advantages and disadvantages in terms of how you interpret quantum mechanics. Mohammed, I see you unmuted. Do you have a question?
Yes, please. Can I ask?
Yes, go ahead.
To clarify the idea in my mind, that means I think U is independent of the orientation of the system. No, not U, omega is independent of the orientation. Orientation. I mean that if, for example, U is a rotational operator, then whatever the orientation of my system, omega is independent of that. It will give me the same measurement.
Yes. So that statement is already true based on the properties of the vector spaces. That if U is a transformation that, say, rotates by 90 degrees, then it acts the same way on any basis vector. So
Yes.
the transformation U might be a rotation around a specific direction, but that's independent of whatever orientation the system was in or whatever vector you started off with.
And omega prime is 2 steps or more operator, which
So
composed
omega
of,
prime is a 2-step or more operator?
yeah, because
Yes.
there's U, yeah.
Yes. So yeah, exactly. So this new operator, which we call omega prime, as you say, consists of 3 steps. First, I transform with U, then I act with the original operator omega that I started off with, and then I transform back.
Then,
So
yes,
yes, it is a 3-step operator.
that's good.
Okay.
In
So
general,
I just wanted to connect these to the words you may have heard before about Schrodinger picture and Heisenberg picture.
yes, in the future we will see that
Yes.
they are the same, but
Yes.
we don't know which one is the right one, because both of them give the same idea, the same results.
Yes. So these are 2 mathematically identical statements, but they differ in terms of our interpretation. And unfortunately, this is the situation that quantum mechanics generally leaves us in, where we have math that works multiple ways to interpret that math and no clear guidance as to what the truth is. So I can't tell you whether the truth is Schrodinger picture or the truth is Heisenberg picture. I suppose I would say the truth is neither, and that by selecting one picture or the other picture, I can make some aspects of the physics obvious at the expense of hiding others. So it will be advantageous to shift around the point of view to make certain aspects of the physics clear for one problem, and then for a different problem, you might want to do a different thing.
Yes, understood that. Thank you.
Other questions?
Yeah, so I had a quick question. So going back to the sigma prime, the unitary operator, it imposes the time dependence on the states.
Yes. So for all that we need to know right now is that time is a parameter that enters U. So to make it a little bit more explicit, my unitary operator as a function of time is something like e to the I Hamiltonian matrix times time.
Okay.
So time is just a number that enters into this, but the Hamiltonian has all the complicated dynamics that describes how it will evolve in time, and then you just evolve it with the Hamiltonian for however much time you want.
So when
It's known as the time evolution operator. Go ahead.
Sorry, so after sigma is then applied, or after the operator acts, the adjoint of the unitary operator then removes the time dependence?
Yeah, so think of it almost like a reference frame. It's like saying, imagine we live in a world of relativity, and you're moving in one direction relativistically, I'm moving in some other direction relativistically, and you want to compare my measurement with something with yours. Your measurement is a different operator than mine is, but I can write your operator as to step first, convert from me to you, your reference frame, that's you. Once I've gone to your reference frame, I perform your measurement omega. Then I perform U dagger to go back to my reference frame.
Okay.
So the measurement on my spaceship is equal to step 1, transform to your spaceship. Step 2, measure it on your spaceship. Step 3, transform back to my spaceship.
Okay.
Does that help?
Thank you. I really like that analogy.
Okay, great. Any other questions? Because this stuff gets pretty abstract pretty fast. Okay, cool. Before I move on, I want to mention one other picture, which is perhaps one you've not heard of before, which is actually the one that is most useful in practice. This is called the interaction picture. And the interaction picture does both. The interaction picture is useful when you're doing perturbation theory. If I have H equals H naught plus delta H in perturbation theory. Usually you want to do this because your ground state Hamiltonian, like your non-interacting Hamiltonian, is easy. I can solve that exactly, and I know exactly what the unitary transformation U is for that Hamiltonian. But the correction is complicated, and that I have to calculate order by order in perturbation theory. And what is extremely helpful about the interaction picture is if you take the states, or the vectors, let's call this U naught is e to the I h naught t. Right, so the full U would have been U equals e to the I ht, where h includes both the free or bare Hamiltonian and the interaction part. I can't solve that, that's too complicated, but if I write e to the I h naught plus delta h t, the h naught piece is easy, that I can work with. And I assign the free or non-interacting part to the states. So it's like saying, I'm going to take A omega B, or let's see, omega prime B prime, and we said that this is A unitary operation omega U B. When I'm doing perturbation theory, it is highly advantageous to split these up, U dagger, so that I have sort of U naught, and then, I don't know, let me call it delta U just for consistency here. There's one-time evolution that comes from the free Hamiltonian, one-time evolution that comes from all the complicated interactions. B. Likewise, this guy I can write as U naught dagger, delta U dagger, A. And we still have the state omega here. So when doing perturbation theory, it is advantageous to take the time dependence of the free states, which is easy, and associate that with the vectors. And so then I get, I'm not even sure what to call it, A naught prime, right? The part that is time dependent, but only with the free Hamiltonian. And then I'm left with delta U dagger omega delta U. And let's say B naught prime. If this is weird and confusing, don't stress out about it yet. We will come back to this much later. But in practice, it is extremely helpful to put the free time dependence in the states, and then all of the non-trivial physics lives in the operators. And then I will calculate the operators order by order, but the states have the trivial time dependence. So not a case of all the time dependence here, all the time dependence there, but you put the boring part of the time dependence in the state so you can ignore it. And then all of the stuff that you need to actually solve associated with your perturbation, you put them in the operators. And so in practice, when you are doing calculations in particle physics or high-level quantum field theory with some perturbation theory that you cannot solve exactly, this is what you do. Okay. Fantastic. So in the remaining 10 minutes of class, let me introduce the eigenvalue and eigenvector problem. I'm sure you guys have seen this and worked with this at some level before, but this is another real example where having something concrete from elementary physics side by side with the highly abstract vector space stuff that we're going to talk about now is extremely helpful. So, okay, being cognizant of the time, let me maybe give you an overview rather than trying to dive in and solve the eigenvalue problem for this specific example now. There's an example that I gave in my undergrad mathematics class when I was introducing the concept of eigenvalues and eigenvectors at the beginning of the semester that I think is helpful here as well, even though it's very elementary for you guys. And that is the example of two coupled harmonic oscillators. I imagine you have already solved this problem in your mechanics classes before. But I think this illustrates very nicely what the physical information contained in the eigenvalue and eigenvector problem is. So for simplicity, I say, okay, I've got two masses. Let me take the spring constants that they're all connected by to be the same. I'm going to measure the oscillation of the system by talking about the displacement x1 of mass number 1 from its equilibrium position, the displacement of mass number 2 from its equilibrium position. You want to write down the equations of motion. So the equations of motion are given by Newton's second law. The equations of motion are easy to write down, in this case from elementary physics, just based on the forces from the spring. If x1 is a positive displacement of the first mass, then that leads to a force minus kx1 on the first spring. On the last spring, if x2 is a positive displacement, that compresses that last spring, and that leads again to a force in the negative direction, minus kx2. The central spring could be stretched or compressed. It depends on x1 and x2. So it will have, if it is stretched, a compressing force pushing it back in, whose magnitude is minus k x2 minus x1 and plus k x2 minus x1 coming from the both sides. So it is straightforward to write down Newton's second law for this problem. I have m x1 double dot equals minus k x1 plus k x2 minus x1. M x2 double dot equals minus k x2 minus x1 minus k x2. This is my system of equations. It is convenient to formulate this as a set of matrix equations. Oops. X1 double dot, x2 double dot equals, let's say, minus k times the scalar matrix 2 minus 1 minus 1, 2, x1, x2. All of the physics of oscillations that goes into this is contained in the time dependence of the left-hand side. That time dependence is actually trivial. If I assume a solution of the form, you take a simple ansatz, x1 of t, x2 of t equals some amplitudes r1, r2, and that they oscillate with the same frequency. Cosine omega t maybe plus some coefficient phi. If you start off with an oscillatory ansatz, you immediately find that A, it does work. It can solve the system of equations. And B, it has the simple relationship that x1 double dot, x2 double dot, just acquire a factor of minus omega squared from x1 and x2. Hopefully this is trivially obvious to see from looking at the form of this equation. If I take two derivatives, derivative of cosine is negative sine, derivative of negative sine is negative cosine. So I go back to the same cosine I started with a minus sign and two factors of omega from chain rule. So that's where I get this. After you plug in that simple ansatz, all of the physics of individual oscillations is done, and you end up with something much simpler. M omega squared over k, x1, x2 equals 2 minus 1 minus 1, 2, x1, x2. Okay, this equation is a very special kind of equation. Only very specific vectors will have the ability to solve this. If I write this thing in our more abstract notation, this would look like m omega squared over k times some vector x equals an operator, a matrix omega acting on state x. This is clearly a very special kind of problem. Not any vector x can do this. When you first write down some vector x, usually when an operator like omega acts on it, it transforms it and gives you a different non-parallel vector. So this vector is omega x. Usually they're different. But for a very special vector, if x is a special vector called an eigenvector, then if I start off with a vector x, for the eigenvector, action of omega does not rotate it. It doesn't point in different directions. It returns something which points in exactly the same direction. Maybe the length changed, but that's all. So clearly this is a very special condition, and not every vector can do this. It's not obvious that there will be any vectors that can do this. If there are vectors that can do this, they have a very special relationship with the matrix omega that transforms them. The critical concept which is present here is that the eigenvectors x which satisfy this are stationary under the action of omega. And I think that concept of being stationary is the really critical part here. In general, if you take this system of masses and you start it off oscillating, the dynamics of how mass number 1 and mass number 2 are coupled are going to mean it's going to look like a very different oscillation dependence later in time than it looked like in the beginning. Right? If I start the whole thing oscillating where, I don't know, this guy's oscillating at one frequency, this guy's oscillating at some different frequency with whatever phase, that's going to be totally destroyed. And at some later time, they're going to have a totally different relationship, different amplitude, different phase. Unless there is a very specific mode of oscillation that is stable under time. If there is an oscillation that's stable under time, if I kick my two masses and start them oscillating in a very specific way at t equals 0, then I will always find them oscillating in the same way at later time. So you can see like the concept of being an eigenvector is about being stationary under the action of some operator. You can see clearly the relation to quantum mechanics, that if that operator is the Hamiltonian, if the operator omega is a Hamiltonian H, H gives you the time dependence of an operator, since H governs time dependence. And so a state psi, which is stationary, which is stationary with respect to the Hamiltonian, is stationary in time. You might call it stable in time. Okay, so we are out of time at this point. So I guess on Tuesday we will go through the meat and potatoes of actually solving the eigenvalue problem, both in the concrete example here, where the matrix is this 2 minus 1 minus 1, 2, and in the more general example where we have some operator omega, and you want to formulate how to find its eigenvalues and eigenvectors. Is the concept clear? Because I feel like eigenvalues and eigenvectors is a specific example where the math becomes very complicated and it's easy to lose sight of the physics. But the physics is incredibly important, and the solutions that give you the eigenvectors and their associated eigenvalues are telling you fundamental emergent properties of a system of coupled degrees of freedom. Okay, so I will cut that off here. Do you guys have any questions or comments for me? Dinup, I see you on pause, or unmuted. Do you have anything to say?
I have a question about the homework.
Okay, great. What would you like to know?
So in problem 2, the last part,
Yes.
yeah. So here it says show that polymetrics together with eigengeometry constitute a vector space over real numbers following. So, so which means we take the polymetrics as basis and then we try to make a vector space, right?
You take the polymatrices as basis, and then what was that second part?
We make a vector space using the polymatrices.
Yeah, so not only the polymatrices, but also the identity matrix,
Yeah.
and those four matrices together, yeah. So I want you to check all the properties of the vector space. Most of them you get for free, coming from ordinary matrix arithmetic. The real exercise there, I think, is going to be proving that the dimension is 4. So that means you need to show that if you try to add a fifth vector, which is linearly independent, you cannot do it. And therefore, that means the dimension of the space is 4.
But the second polymatrix is a complex one, right?
Right. So the sigma 2, the second polymatrix, is complex. I mean that the scalars that I'm going to multiply them by are real scalars.
So
Yeah, but if you multiply by a real scalar, you don't get a real vector space.
It is a vector space over the field of real numbers. The basis vectors themselves are complex, but the real numbers that you can do scalar multiplication with are real. maybe I'm not understanding the question. If you want to come to my office hours in a few minutes, maybe you can explain in more detail. Maybe I didn't think carefully through that one. If there's some problem that I didn't foresee, then I will say, let's imagine that the vector field